My name is Alexandru Gabriel, and today I will present to you an interesting approach to generate code from a natural language description using quite a new concept called the abstract syntax graph. In this presentation, first of all, I will describe to you the task at hand, followed by briefly explaining the state-of-the-art methodology for generating code in the form of an abstract syntax tree. Afterwards, we will see what is our concrete contribution in this field and introduce a new concept, the abstract syntax graph. To generate such a graph, we will need to go through a graph neural network, which later introduces the graph recurrent neural network. And in the end, we will see some results followed by discussion of them, some concluding remarks, and some possible future work in this field, so stay tuned. First of all, let's describe our problem. Code generation from natural language is the process of creating source code from a natural language text. And as an input, usually have some sort of text which represents an abstraction or summarization of the code. And the output is represented by a section of code. And depending on the case, it can either be just a fully runnable program or a smaller section of code that handles just the logic that the user needs. In the literature, things are more straightforward when considering the data sets used. They are usually trading card games like Hearthstone, for example, which you might recognize from this card right here, or Magic the Gathering. And these cards mostly are used because they contain standardized text, and that text explains the mechanics each card has. And these mechanics can be mapped to code. For example, if you take this card, draw cards until you have as many in hand as your opponent, what the code does is computes the difference between the length of the player's hands, and for each of these differences, the player draws a card. So it's straightforward. From some points of view, this task is quite similar to a machine translation task. Yes, we basically want to get the equivalent from one language to another, which in our case is natural language to machine language. Moreover, this task is usually solved using sequence-to-sequence models, which are based on a recurrent neural network, in order to handle the varying length in both input and output sequences. For evaluation, things are inherited from that machine translation task. The metrics used are usually the token accuracy, which it's pretty straightforward, and as well as the blur score, which in short depends on the context of the generated text. And before we dive into the state-of-the-art approach, let's first discuss the concept of an abstract syntax tree. This abstract syntax tree is a tree-like representation of the code. Instead of the text, it's a hierarchical structure that represents the relationships in the code, and it can be converted to and from code quite easily. On this slide, you can see a section of the code that computes the greatest common divisor. And on the right side, you can see the abstract syntax tree. We have a root node statement sequence, which has, in this section of code, we have two statements, a while and a return. And that while has a condition, b different from 0, and the while has a body, which contains that if this is branch, and things just go straight forward from this. So to summarize this approach, instead of text like in a translation task, we'll generate a tree, more specifically the abstract syntax tree. And this way, we are guaranteed to generate no syntax errors, but the model becomes a bit more complicated because it requires more additional information to convert from the text into a tree. So in order to generate a tree, the model needs the initial description, which already has from the initial problem. It also requires a state and previously generated node, which are needed by the recurrent network by default to work properly, and the parent node, which incorporates the idea of generating a tree. And the architecture used is called an encoder-decoder. It's called encoder-decoder. And the intuition behind it is that the encoder codes the information, the input information, so that the model understands it, and then the decoder comes in and translates the information from the internal model's intuition into that output sequence. This architecture can be seen on the top right side of the screen, which has an input from x0 to x2, which everything is encoded. Some computation is done inside that hidden state, and then the decoder comes in and generates 4 tokens instead of 3 from Y0 to Y3. And as compared to other machine learning models, this single-core architecture has an advantage that we can handle both input and output to be varying. And it's good because in our problem, both the input text and the output sequence has a varying length of words. The aforementioned these dependencies can be seen better in this figure, where a node depends on its parents and on the previously generated node. The input to this is to sort my list in a descending order, and the output code is just sorted out of my list with a reverse equals true. How this works is that we know that our code has to start with a root node, and then that root together with the description goes through our model and generates the expression node. Things are done the same for that expression to call node and so on until the first branch of the call node is generated. Things get more interesting from down here because now this expression to expression node depends on the call and on the lastly generated node, which is this one right here. So with the usage of a parent node and the previously generated node, we can pinpoint exactly to which child we are trying to generate which node from. And this generation is possible mostly because of the tree's hierarchical structure. In the abscess syntax tree, each edge represents a dependency in the code. For example, this while node has a condition which is represented by this compare node and a body represented by this branch node. And because of this structure, we can easily reconcile the code from the depth first search order if we add some tokens for listing. If you take the abscess syntax tree from the left, we'll start off with the root node, which is statement sequence. And we know that statement sequence has a list of nodes, has a list of statements. So we just append a list start token. We go on the left branch with a while. While has a condition, which is not a list, so we don't have to append any token. We have that compare, B compares with 0. And then we have this body. This body is usually a list, so we append this list start token, branch, and so on until we finish the first branch from the statement, the sequence. Then we return to this return node variable name A, and because we finished creating a list, we will append this list and token. Though this approach is considered state-of-the-art, it still has some weaknesses. So yeah, first of all, the recurrent neural network becomes less accurate the more tokens it generates. Moreover, this generation process has some redundancies, which are highlighted in the red circles. We can see that there are many variables with the name B and A in this syntax tree. And if any of these variables is to be misgenerated, for example, we put a random C somewhere where a B was, the whole code will have another meaning, and it might make the debugging and the development process implicitly more time-consuming. So this generation of the leaves is way more expensive than the generation of other node types. All right, so what we propose are some ways to solve these issues, and we'll do so by introducing a new concept called the syntax graph, which will be used as the output of a graphical neural network in order to generate, instead of an abscess syntax tree, the abscess syntax graph. So what is this abscess syntax graph, you may wonder? Well, it's quite similar to the abscess syntax tree, but it has some features that high-level programming language do at runtime. Such features include the variable pointers to memory locations, which we can incorporate in the tree with loops to uniquely create leaf nodes. And to generate such a graph, because a depth first search order would not return all the information contained by the graph, we have to rely to other mechanisms which use the graphical neural network capabilities. On this side, you can see a comparison between the f-syntax tree and the f-syntax graph representation, where the graph will contain only the first apparition of each leaf node. And if an existing leaf is referenced by a node, the graph, for example, we have this compare statement, which has a reference to variable B initially, but in order to transform it to a graph, we added this edge and removed the second repetition of variable b. Moreover, we consider this graph to be directed simply because it can better showcase the relationships within the code. So the algorithm to construct an empty syntax graph from an empty syntax tree is quite simple. First step is to iterate each existing edge and give it a direction from the parent to the child, because we mentioned that we want to make a directed graph. And the second step is to iterate all the leaf nodes in the depth of search order. This order doesn't matter that much. It has been chosen just because of its serialization and deserialization from the syntax tree, but it can be even depth of search. If the current leaf node already exists in the syntax tree, then just delete that leaf node from the tree and create an edge from that parent to the pre-existing leaf node. Otherwise, the node remains, and if everything goes right, something like this should be the output from our code. All right, we've seen what we want to generate, but how will we do it? Well, for that, we first have to look at the graph neural network. A graph neural network is a type of artificial neural network that can process information structured as a graph. So as an input, it has some graph with some node features and edges. And as opposed to classical neural networks where there is a forward propagation and a back propagation, this graph neural network has a message passing stage where each node receives information from neighboring nodes, independent of the order of the nodes, and an update state, where each node updates the information based on the aggregated information. And the output layer is task specific, so it's similar to a regular neural network. And to properly generate a graph, we will use a special kind of graph neural network called graph recurrent neural network, which functions similarly to a recurrent neural network from the point of generating the output sequentially. So the graph has two components, nodes and edges. Each node will be generated one step at a time, and the edges will be generated in the form of the agency matrix, one line in the matrix at once. In this picture, we can see that the graph is currently the step t-1 with 4 nodes generated, and want to generate nodes 5 and 6. And so we do that, and we also get the agency matrix rows. And we can see from this figure that 5 has an edge with the second node, and 6 has 2 edges, one with the first node and the second with the node 5. And the results after incorporating everything are quite disappointing, to say the least, because we achieved 4 times lower node type accuracy. And by the way, this doesn't contain any typos or anything. The below score is really close to 0. So you can expect that the order of generated nodes is a permutation of the target nodes. And because the edges in an empty syntax graph are very, very sparse, the edge accuracy is almost 0. The edge accuracy is almost 1, while the precision is 0. So to reason these results, though we took special care when constructing the empty syntax graph to consider the order of the children, the graph neural network does not, which explains these results. And because of this order not being respected, the output code cannot be properly reproduced. Moreover, the empty syntax graph has sparse edges. And because of this sparsity, the generated nodes are mostly isolated, even though the output might be a permutation of the ground truth. And to conclude this approach, this concept of empty syntax graph, although it is a graph by name, in properties it's not. In a graph, there is no order in the nodes, while this empty syntax graph, the order is everything which allows the deserialization and serialization from and to code. And moreover, the graph neural networks do not seem appropriate for code-related tasks, since the order of the operations in code matters, and in a graph neural network, the graph neural network cannot consider this order of operations. But the current approaches still have weaknesses, and identifying them will always be the first step in finding their solution. As for the future work, as the empty syntax graph is quite sparse when considering the edges, I propose that we should look at other correlated graph structures which are more condensed, meaning that they have less nodes and more edges. And such a graph is called a code property graph. And it represents a combination of multiple graph-related structures, such as the API syntax tree, control flow graph, and many, many more. And we can study how to generate from a natural language text such a code property graph. The only issue with this type of code representation is the fact that it's almost impossible to deserialize code from the code property graph, because two sections of code totally different might have the same code property graph. So this function of converting to a code property graph is not injective. So it's not bijective nor invertible. So we have to research for ways to properly construct the code from such a graph. And such a graph example can be seen on this slide, where we have this root node implementation. We have some FSindex edges, and although this graph is not quite intuitive, we don't have all the information required to read it, we can see that we have an if statement right here, which has an edge with a data flow graph with some argument equals something, where argument calls equals. We also, regarding this if node, we have an then statement and an else statement. And we can see that various functions are called on argument.length, trim, and so on. And this was my presentation. Thank you for your attention. Do you have any questions?